Very good afternoon, everyone. Today we are going to discuss the second lecture in the module 2, that is computation of uniform flow. So in the first lecture, we studied about the uniform flow, its establishment, various resistance equations like the Chase's equation, the Manning's equation, and the factors on which the Manning's roughness constant depends upon. So that is what we discuss in that class, and that will be carried forward in this lecture as well. So the learning objectives for this lecture are: we'll derive the section factor and hydraulic exponent for uniform flow computation, we'll analyze the types of problem in uniform flow computation, and we will compute the normal depth for various channel sections. So continuing with the Manning's equation, so the Manning's equation can be expressed as Q is equal to V into A, that is the continuity equation, and V, where V is represented as 1 by N A R raised to 2 by 3 S naught raised to half. Now this term can be again simplified as Q is equal to K into S naught raised to half. Now the term K that denotes the conveyance of a channel section. So K is equal to 1 by N A R raised to 2 by 3. So this particular term in the Manning's equation, that is substituted by K, and that is called conveyance of channel. So if we look conveyance, so that is Q upon under root S naught. So conveyance is the carrying capacity of channel per unit longitudinal slope. So that is the definition of conveyance. Now, again reflecting to the above equation, so in the conveyance equation, the term A R raised to 2 by 3, we can see that term, that is a distinct function of your flow depth. So it is a distinct function of your flow depth. So that particular term AR is to 2 by 3 is called the section factor, and it is a very important element when we are computing the uniform flow. So since it is dependent on the flow depth, so indirectly it will depend upon the geometry of the cross section. So modifying the Manning's equation, we get AR is to 2 by 3 is equal to NQ upon under root S naught. So on the LHS, that depends upon the geometry, and RHS depends upon the flow rate, roughness, and the longitudinal slope. So this is how the section factor is interpreted. Now the next and very foremost important aspect, that is a normal depth, which we are going to understand. Now in the above equation, where we discuss the section factor AR is to 2 by 3 is equal to NQ upon under root S naught. So if we try to solve that equation, so we can see for given conditions of your N, Q and S naught, you will have only one possible depth which will be there for maintaining the uniform flow, given that the value of AR is to 2 by 3 will always increase with the depth. So for the conditions where our section factor AR is to 2 by 3 is a monotonically increasing function of the flow depth Y, in that case, for given flow conditions, you will have a unique depth, and that depth is called the normal depth. Okay, so that is very important term. So when N and S naught are known for a channel section, only one discharge is possible for maintaining the uniform flow, so indirectly maintaining the normal depth, and that discharge is called the normal discharge. So the discharge which is maintaining the normal depth is called the normal discharge. Now let us understand the kinds of channels and cross section properties. Now the channels are broadly classified into two, that is channels of first kind and channels of the second kind. What is the difference? The channels of the first kind are those where AR is 2 by 3, that is section factor, would monotonically increase with the increase in depth. So as the section factor increases, the depth will increase. So they are related that way. But in the channels of second kind, the section factor is not a single valued function of the depth. That is, more than one values of depth can also be possible when you are dealing with the channels of second kind. Now in channels of first kind, this relationship is true for any channel shape whose top width is either constant or increases with depth. So if we take into consideration the rectangular channel, the top width is constant. If we take a trapezoidal channel, the top width will increase with depth, or even a triangular channel. So that is the case in channels of first kind. Now, channels with a closing top width can be designated as a channels of second kind. So, a circular channel section can be a channel of second kind where the top width is closed. Even a square channel section where the top width is closed, that can be a channel of second kind. Now, uh, in channels of first kind, there is a unique depth associated with each discharge, and in channels of second kind, for a given discharge, more than one depth of flow exists. So the examples are also given. So you can see the examples, that is for the channels of first kind. You have rectangular, trapezoidal, triangular, semicircular sections, and channels of second kind, you have circular or ovoid sievers or delta shaped channels. So these are the channels of first kind, and these are the channels of second kind. So the delta shape, this is a circular section. So circular section is a channel of second kind. And corresponding to the section factor and the aspect ratio, different curves are being given so that we can analyze the variation in the depth. If we can also calculate by the formula. If not, we can use these curves. Now that brings us to a discussion question, that in this case of a trapezoidal channel, that is in figure A, so there is a factor called M. So what will happen, or the resulting cross section, if M is made 0? So if the side slope is made 0, what is the resulting cross section? Second, if your bottom width, if that is made 0, then what is the resulting cross section? So that is the thing which you need to ponder upon and give the answers. Okay, now we will see which are the various geometrical shapes and their hydraulic characteristics. So coming to the first geometrical shape, there is a very basic shape, that is rectangular. Now let us understand the nomenclature. Y stands for the flow depth, capital B stands for the bottom width, and capital T stands for the top width. So the top width here, so we'll calculate all the elements. First element is top width, so that is B. Second element is flow area A, so that is B into Y. Third element is wetted perimeter P, so that is B plus, now this is the wetted perimeter, this, so this is B plus 1 and 2 times Y, so B plus 2Y. And next is hydraulic radius, R is equal to A by P, so ratio of A and P. And hydraulic depth, that is the ratio of A by T, so area by top width, so that is B, Y by B, so that is you get is Y. Now let us derive for the trapezoidal section. Now trapezoidal section, you have been given a side slope of M is to 1, so the top width will be bottom width plus this much. So this is the additional, so the bottom width is B plus, when you take the triangle and solve, so this much portion, that is M into Y, so B plus My and My, so that becomes B plus 2My. Now if we go to the area, so area of flow will be, so you have the total area of flow that you can compute with the help of geometry, that is B plus My into Y. So that is your area of flow. Then you have wetted perimeter. Now wetted perimeter, that is this thing, so you have the bottom width as constant. Now 2 times this side slope you have to compute, this side slope. So this side slope, when you compute, so that comes out to be Y into under root M square plus 1, where M is your side slope of the channel, and since it is considered 2 times, so that 2 factors comes into consideration. Okay, now hydraulic radius and depth you can compute likewise. Next is the triangular section. Now you have been given this angle theta. So either you can compute in the terms of you can take this as divide into 2 and take this as theta by 2 and also proceed with the computation, or simply you can take it as m and then you can have the triangle and properties, and based on that you can compute. So the top width is 2 into my. Okay, so top width is 2 because here the bottom width is not there. So that is an improvisation in the trapezoidal section. You remove the bottom width, so you get just 2 into my is a top width. The area is my square. So in the trapezoidal section, if you put b is 0, you get what is there for the triangular section. And if you want to derive for the rectangular section, what you can do, you can put this as 0, so you get whatever is remaining for the rectangle. So trapezoidal section is the ideal section. If you know the properties, you can derive for the rectangular and triangular automatically. Similarly, the triangular section, the wetted perimeter is 2y under root m square plus 1, and the hydraulic depth is y by 2. So these are the properties for the rectangular, trapezoidal and triangular section. So we can move ahead to other sections, that is a circular section, semicircular section and the delta shape section. So the circular section I'm not discussing right now, that we will derive it later. So I'm just skipping it, but I'll just explain the term that d is the diameter of the circular section, and 2 theta is the angle subtended by the water surface at the center, and y is the depth of flow. So even though it is a closed section, it will not flow completely full, it is partially full only. Coming to the semicircular section, whose top width is d, that is the diameter as well, and the depth of flow, if it is half full, so it is d by 2. So based on that, you can derive the top width as d, area is pi d square by 8, wetted perimeter, since the circumference of circle is pi d, this is a semicircle, it is pi d by 2. Likewise, you can compute other properties. Now the last is the delta shape, where the slope is very interesting, it is minus m because it is a negative slope. Okay, so it is minus m, so that is instead of b plus 2my, it becomes b minus 2my. So assume a trapezoidal section but with a negative side slope. So this trapezoidal section has a side slope m, but this is a negative side slope minus m. So that is how it can be derived. So these are the characteristics of some general shapes which can be derived. If there is an any other shape, then you can, by the geometrical knowledge, you can derive it. Now we'll go into depth about certain cross sections while computing the normal depth. The very first one is a wide rectangular channel. Now what is a wide rectangular channel? A wide rectangular channel is one where the width is very vast as compared to your uh, side, as compared to your depth. So in this case, this yn, that represents the normal depth, b represents the width of the channel, and now area can be given as b into yn. The wetted perimeter can be given as b plus 2yn, and the hydraulic radius r is equal to a by p. Now what happens in case of a wide rectangular channel? In case of a wide rectangular channel, your b is much greater than yn. So when your b is much greater than yn, so what happens? This term is very negligible. So your wetted perimeter is just width. Okay. Now here the multiplication will be very small, so that doesn't matter. But here it is addition, so we are neglecting it. So coming to this term r, so here what will happen? This term will be neglected. So r becomes b yn upon b, and thus r is equal to yn. So for a wide rectangular channel, your hydraulic radius is essentially the depth of flow. Now let us understand the computation of normal depth for such case. So we'll go by the standard, that is the Manning's equation. So in Manning's equation, let us substitute all the parameters. So you are well aware with it. So a is b into yn. Now r is equal to yn. So simplification is that qn upon b under root s naught is equal to yn raised to 5 by 3. So if you want to solve for yn is equal to small q n upon under root s naught raised to 3 by 5, where small q is capital Q by capital B, that is discharge per unit width in the channel. So that is represented as meter cube per second per meter width. So this is the expression for normal depth in case of a wide rectangular channel. If it is specified that it is a wide rectangular channel, then only you have to go for this formula. Now coming to a rectangular channel which is not a wide one, which is a narrow rectangular channel, that is based on the aspect ratio yn by b. So that criteria comes into picture. So again, you know the geometric elements, a is equal to b by n, p and r. So let us substitute all this into Manning's equation. So we have q is equal to 1 by n, b y n into b yn upon b plus 2 yn raised to 2 by 3 and s naught raised to half. Simplifying it, we have q is equal to 1 by n. Now this term will be, the power law comes into picture. So it is b yn raised to 5 by 3 and b plus 2 yn raised to 2 by 3. Let us simplify it. Let us take all the yn terms on one side and other terms on the other side. So we have qn upon under root s naught b raised to 5 by 3, that is equal to yn raised to 5 by 3 upon b plus 2 yn raised to 2 by 3. Now this equation is a bit complex in nature, so you need to solve it by trial and error to get the value of n. So what you can do, you can compute the LHS because all parameters are given for LHS, and for RHS what you can do, let us say you assume the value of yn you take it as 1, then solve the RHS, whether LHS is equal to RHS, no, then take another higher value, yn equal to 1.5. based on the solution is converging or diverging, you can take the trial values of yn, and at the value of yn when LHS is equal to RHS, that will be your normal depth in that particular case. Okay, so for trapezoidal section, I'm not discussing in detail because it is again straightforward on the same way. I'll discuss about a circular section because it is a bit challenging. So let us understand the circular section. Now, for the circular section, the geometry, this is the diameter of flow d, diameter of the channel, sorry, d, the depth of flow y naught, or it is represented as yn as well. That is different nomenclature in different textbooks. R0 is the radius of the channel, and 2 theta is the angle subtended by the water surface. So this is the water surface at the center in radians. So this angle is in radians. So the area of flow, so this is the area of flow you want to compute. So what you will do, you will take the area of this sector OMN, and then you will subtract the area of triangle OMN so that you can get this area. So that is what we are doing here. So area of sector is half r naught square 2 theta, that is the area of sector, and area of triangle, that is half 2 r naught sine theta into r naught cos theta. So with the help of this, you can find the area of this triangle and just multiply by 2 so that you get the area, or simply you can have half base into altitude. So this is your base and you can compute the altitude as well. Simplifying it, we have half r0 square 2 theta minus r0 square sine 2 theta. Now r0 is d by 2. So putting this in this equation and taking common, so you have area as d square by 8 into 2 theta minus sine 2 theta. So this can be simplified as sine 2 theta. So that is what the expression were mentioned in the table, but we can derive in this particular fashion. Now coming to the wetted perimeter, P is equal to 2 r naught theta, where 2 into r naught is d. So that becomes d theta. And if you want to find out this angle theta, so you have cos theta is equal to r naught minus y naught upon y naught, and that is equal to 1 minus 2 y naught by d. So that way you can find out this angle theta also if this information is given to you. Now what we'll do, we'll apply the Manning's equation and try to find the normal depth. So when we are applying the Manning's equation, we'll substitute the parameters A, P, and then R. So we'll bring the other things to this side. So Qn upon under root S naught, that is equal to d square by 8 2 theta minus sine 2 theta, that is the area, and this is the hydraulic radius. When we simplify, it becomes d to the power 10 by 3 2 theta minus sine 2 theta raised to power 5 by 3, the whole divided by d raised to 5 by 3 and d theta raised to 2 by 3. Now here, if the theta is known to you, so only unknown is d. Now when the unknown is d, so what you can do, you can compute d using this equation, and then you can use this equation 7 to compute the term normal depth. So that is how you arrive at normal depth for the circular section. Now again, it may involve some trial and error procedure while you are adopting this form of equation. There are certain charts and tables readily available, but that is for the field use. When you are doing an academic exercise, you will always go by this trial and error method, because in your competitive exams as well, they don't provide the charts and all. Now, as we saw that the circular sections are the channels of second kind. So channels of second kind have more than one depth for a given discharge. So let us understand that. So continuing with that circular section. So here, this is the two discharges are there. Q is the discharge at a given depth, Y, while QF is the discharge at y is equal to d. When y is equal to d, that means your channel is flowing full. So when the channel is flowing full versus the channel flowing partially full, that two ratios are taken and a non-dimensional constant is arrived. Similarly, velocity when your channel is full, channel is partially full, to the velocity when channel is full, that non-dimensional parameter is arrived. And we take another non-dimensional parameter, that is the ratio of depth of flow to the diameter of channel. So what we observe that uh, unless some point you can see that it is a monotonically rising function, but after one point it starts to decrease. So let us say if your for a given value of y by d, let us say my y by d is 9, or let us take the reverse case. If your ratio of discharge is 1.05, so for this condition or anything greater than 1, you can see what it does, it intersects at 2 points. So you can get two normal depths, and that is called the multiplicity of normal depths corresponding to a single discharge. Similar behavior is observed for the velocity as well, that if you take any point, let us say I'm taking this particular point, so I'm getting two offsets, and that corresponds to two normal depths for a given velocity, and that could cause issues while you are designing the flow, whether you have to consider this normal depth or this normal depth. So there are constraints in that particular case. So we will discuss while designing the channel that which normal depth to consider, so that I'll leave for the next lecture. But here we are understanding that the channels of second kind have the condition where the multiplicities of normal depth occurs. Now the maximum discharge occurs at a y by d ratio of 0.938. So here is where somewhere the maximum discharge occurs, and the maximum velocity occurs at the ratio of 0.8128, so somewhere here. So there the maximum velocity occurs. Now, based on this graph, the discussion question is there. Is there any limiting value of discharge that can be passed through a circular section? Let us say you want to avoid the multiplicity of normal depth. So in that case, what can be the limiting value of discharge that can be safely passed? So that is what you need to answer. Okay, so moving ahead, we can also compute what is the maximum discharge and maximum velocity in the channels of second kind. Now, if you want to find the maximum velocity, so that condition would be arising where your dq by dy, that is 0. So we have that equation, and we'll just equate it to 0. Now here we are taking some assumptions, that is the Manning's n is assumed to be constant at all depths, and the bed slope is also constant. So that terms are eliminated. So in the Manning's equation, what is left? AR raised to 2 by 3. So we'll just differentiate it with AR raised to 2 by 3, and what we get, that is d by dy of a square by p square. So if you put the values with respect to that and differentiate the equation, you can get the condition of maximum discharge. Now since your AR raised to 2 by 3 is a function of Fy, that is a function of y, so for a given channel geometry, this equation will be helpful to evaluate the depth for a maximum discharge. Similarly, we can derive the condition of maximum velocity as well. So while deriving the maximum velocity condition, we'll again follow the same process where dv by dy is equated to 0. Now in the Manning's equation, we again assume that the Manning's n is constant for all depths, bed slope is 0. Okay, so the condition of maximum velocity, that is dr by dy, because in Manning's equation you don't have a, so dr by dy is 0. What is r? R is a by p. So when you differentiate equation, that becomes because both are a function of y, so you go for a partial differentiation, so that is p into dA by dy minus a into dp by dy, that is 0. So both are function of y, so if you solve this equation for a given geometry, you can get the depth for maximum velocity. So that is how the depth can be arrived. So these two are very important equations when you want to compute the depth and velocity for maximum flow condition. Coming to the last part, that is the hydraulic exponent for uniform flow computation. Now we already discussed what is conveyance. So conveyance is a function of depth of flow. Okay, k is equal to AR raised to 2 by 3 by n. Now uh, let us assume or let us express that particular thing, that is k square is equal to c into y raised to n, because it is a function of depth. So c is a coefficient and n is the hydraulic exponent for uniform flow computation. So you want to estimate this. So what we'll do in this equation, we'll take log on both the sides and then differentiate with respect to y. So when we take the log on both the sides, so it becomes d by dy of ln k, that is equal to n upon 2y. So that is equation 13. Now we already know that the conveyance k is equal to 1 by n AR raised to 2 by 3. So this equation also will do the same procedure. We will take the log on both the sides, differentiate with respect to y, but here we take a small assumption that the Manning's n is independent of y. In actual, it is not, but we are taking an assumption to simplify our case. So we'll again take the log. So it is d by dy of ln k, that is 1 by a dA by dy plus 2 by 3 1 by r dr by dy. Now dA by dy is well known as t, that is top width, and r is equal to a by p. So again, rearranging and simplifying the equation, we get d by dy of ln k is equal to 1 by 3a phi t minus 2r dp by dy. So this is a simplified form. So you can process it in 2 steps, you will get this simplification. So we'll compare equation 15 and 13. So we get n is equal to 2y by 3a into phi t minus 2r into dp by dy, and this is your hydraulic exponent for uniform flow. So if you are given any channel geometry, let us say you are given a trapezoidal section or rectangular section, you can compute this hydraulic exponent n for that given channel section. Okay, so this brings to a question that what would be the value of hydraulic exponent for a wide rectangular channel. So for wide rectangular channel, you can easily know what are your channel properties, that is A, R, P and all, and then you can simply compute the hydraulic exponent based on that. Also, there is a curve which is available that will provide you the hydraulic exponent for different channel geometries. So this is a trapezoidal section and a circular section. So we can see that a trapezoidal section, if the side slope that z is 0, so you can follow this curve. If the side slope is 0.51 and different levels, then you have different curves which are prescribed for that. Okay, so that can be adopted. and lastly, if you have the circular section, then you will adopt this particular curve. So that is how you can compute the values of hydraulic exponent. So that's all for today. In the next lecture, we will discuss about the design of channel section for uniform flow considerations. So thank you very much. Have a nice day.